Section 4.2, Adding and Subtracting Matrices. In this section, we're going to talk about some basic addition and subtraction of matrices, and then we're also going to look at solving matrix equations that involve the operations of addition and subtraction. The first part, talking about adding and subtracting matrices, we have a few rules as far as being able to add matrices together or subtract them. The first is that they have to have exactly the same dimensions. So if you look at my examples below, the first pair of matrices that I am adding together have dimensions of 2 by 3. If you remember from the last section, we calculate the dimensions by taking the number of rows by the number of columns. These matrices have 2 rows and 3 columns each. In my second example, you'll notice that the matrices both have 2 rows and 2 columns. So we would call those 2 by 2 matrices. Secondly, when we get ready to actually do the addition or subtraction of our matrices, we are simply going to add and subtract the corresponding elements in the matrices. So in other words, the element that's located in row 1, column 1 of the first matrix will be added or subtracted, depending on your operation, to the element that's in row 1, column 1 of the second matrix. Your resulting matrix, or in other words, your answer, your sum, or your difference, will be a matrix that has the same dimensions as your original, since you are obviously matching up row for row and column for column each of the elements. So I'm going to go ahead and do the addition in the first pair of matrices. So according to what I have here, first of all, they do have the same dimensions, so I'm able to add them together. I'm going to match up corresponding elements, meaning that row 1, column 1, I'm going to match with row 1, column 1 in the second matrix. So in this case, 1 plus 3 is going to give me a 4 as my first element. And I'm going to continue this pattern all the way through the rest of my elements. So if I finish up the first row, column 2, negative 2 plus 9 is going to give me 7. 0 plus negative 3 is going to give me negative 3. Move down to the second row. 3 plus negative 9 is negative 6. Negative 5 and 6 is going to give me 1. And 7 and 12 will give me 19. So the sum of those two matrices results in the matrix that has 4, 7, negative 3, negative 6, 1, and 19 as its elements. Now if I move over to my second example, same process. My operation is going to be subtraction this time. And what I want to do with these is, again, match up the corresponding elements. So when I look at this matrix, it starts with negative 3 as row 1, column 1, and negative 3 as row 1, column 1 in the second matrix. This operation happens to be subtraction. So the only caution that I have for you here is to be careful with your subtraction and your signs and make sure that you're doing your subtraction correctly. So negative 3 minus 3 is actually going to give me a 0 as my first element in my matrix. In row 1, column 2, a 5 and a 1, I'm doing subtraction. 5 minus 1 leaves me with a 4. Second row, negative 1 minus 2 is actually going to leave me with a negative 3. And lastly, 10 minus negative 4 is actually going to end up being a positive 14. So this matrix has the same dimensions as my two originals, a 2 by 2, and this would be the difference of those two matrices. So adding and subtracting matrices, again, we're just going to add or subtract the corresponding elements to get our resulting matrix. Now, as far as addition goes with matrices, there are a few properties that we normally have with addition that also apply to matrices. For example, the first of those is closure. When we talk about closure, remember, just simply says that if I take two matrices, A and B, and I add them together, my result is still going to be a matrix. In other words, I can't add two matrices together and get an answer that's not a matrix. Our second property, which is the commutative property, which we also already have for addition, says that I can add matrices in any order. So I can add matrix A plus matrix B, or I can put matrix B first and then add A, and it's the same answer. Third, we also have the associative property, which again applies to regular addition. It applies to matrices. It doesn't matter what order I add my matrices together. If it's all addition, they will all come out to be the same final matrix. The next property is that there is such a thing as an identity matrix, where if you take a matrix and you add it to the identity, you will simply get that matrix back as your answer. Okay, and if you think about the identity matrix, what would I have to add to every element to make it an identity? Well, if I had a 2 by 2 matrix, it would simply be a 2 by 2 matrix of all zeros, would be my identity matrix. Now, the inverse matrix is a little different because obviously I have to have the opposite of every element. But again, an inverse matrix exists where if you add a matrix to its inverse, you will get the identity matrix. You will get a matrix of all zeros, just like when we do addition with a regular inverse. Okay, so these properties, closure, commutative, associative, identity, inverse, all apply normally to addition, and they also apply when we add matrices. Now, the second thing we said we were going to focus on was solving a matrix equation using addition and subtraction. So now that we know how to add and subtract matrices, we're actually going to use that to solve an equation. So a matrix equation is simply an equation that involves the use of matrices, and your answer to your equation, instead of being a number or an ordered pair like we've had in the past, is actually going to be a full matrix. So one thing for you to think about before we start this, just some basic review here. If I have an equation that looks like this, x plus 3 equals 9, what operations do I do to solve this problem and why? If you think about it, when you first learned to solve a single step equation like this, you talked about the properties of equality, that whatever you do to one side of the equation, you have to do to the other. Okay, so that's going to be true with our matrix equations. And in an equation like this, if I have x plus 3 equals 9, I would probably choose to subtract 3 from both sides, again, keeping my properties of equality, so that I could get x by itself. Okay, well, when I solve a matrix equation, like the two I have here, the process is still the same. It's an addition. You have, this equation is asking me the matrix x plus the matrix negative 1, 0, 2, and 5 is equal to the matrix 10, 7, negative 4, and 4. So what I'm simply trying to do is find out what is matrix x that I can add to the matrix negative 1, 0, 2, and 5, so that I get 10, 7, negative 4, and 4. Okay, so like the example that I had up here previously, okay, the x plus 3, my equation down here looks sort of similar to x plus 3 equals 9. And I said that I would subtract 3 from both sides of my equation. So in this case, I'm going to use the same principle because I'm adding these two matrices together. I'm going to use subtraction to, quote, undo this addition so that I can solve this equation. So I'm using subtraction, and what I have to subtract instead of subtracting an entire, or subtracting a number, is I have to subtract a whole matrix. So I'm going to subtract the matrix from both sides, negative 1, 0, 2, and 5. Okay, so over on the left-hand side of my equation, like would normally happen, these two matrices are going to make 0, or they're actually going to make the identity matrix of all zeros. And according to my properties of matrices that we just talked about on the previous page, the identity matrix, if I add it to anything, is going to equal that matrix. So in other words, most of the time we refer to this as they cancel each other out, and I end up with just x on the left-hand side of my equation. Now, on the other side of my equation, though, I actually need to do the subtraction. So I'm going to take my corresponding elements, like 10 and negative 1, and I'm going to subtract. So 10 minus negative 1 is actually going to give me 11. Okay, then I'm going to go on to the rest of my elements. 7 minus 0 is still going to be 7. Negative 4 minus 2 is going to give me negative 6. And finally, 4 minus 5 is going to give me negative 1. So my final answer for my matrix is this matrix down here, where it is 11, 7, negative 6, negative 1. Okay, so I'm going to apply this principle to this second equation over here, this second matrix equation. Change my color here just for a minute so we can tell the difference. Okay, so on this equation, you'll notice it does have subtraction in the middle, but what I want you to notice about the subtraction is that the subtraction is referring to the x. It's actually the x that's being subtracted. So what I'm going to do here is I actually am still going to use subtraction to move my matrix from one side to the other, because this matrix has nothing in front of it. So I'm end up doing subtraction again, -3, 1, 2, -4. So I subtract that from this side. And then I'm also going to subtract that from this side over here, -3, 1, 2, -4. Now what happens, if you think about this, what would happen in a normal equation, right? The x is still going to have the negative sign. Okay, these two matrices, like we said, quote, cancel. Okay, they make the identity. So 0 minus x is just simply going to give me -x. Now I am going to go ahead and subtract my matrices over here on the right-hand side. So -3 minus -3 is going to give me 0. And then 5 minus 1 is going to give me 4. -1 minus 2 is going to give me -3. And 10 minus -4 is going to give me 14. However, now, if I'm looking at this problem, I am not quite finished with it yet. I still have the opposite of x, or -x. So if the opposite of x equals the matrix 0, 4, -3, 14, I need to come up with what's the opposite of this matrix. Okay, so again, or you can think of it as multiplying by -1. So we're going to take everything in our equation, or sorry, our matrix, and we're going to multiply by -1. So that's going to give me 0, because 0 times -1 is still 0. -4, +3, and -14. So x is equal to 0, -4, 3, and -14 for my matrices. Okay. Finally, we're going to take a look at finding missing elements or finding variables within elements. And we do that when we have two matrices that are equal to each other by noting that when matrices are equal, their corresponding elements must be equal. So what that means is whatever is in row 1, column 1 in the first matrix has to be equal to row 1, column 1 in the second matrix. That's what makes matrices equal. And I know these two matrices are equal simply because they have an equal sign between them. Okay. So here's what I'm going to do. And you'll notice, like if you look in row 1, column 2, you have a 4, and row 1, column 2, you have a 4 in your other matrix. So to find the missing variables, if I'm looking for x, here is 2x minus 5. And since I know that my matrices are equal, I know that that has to be equal to its corresponding element, and its corresponding element is 25. So what I'm going to do, this particular matrix tells me that 2x minus 5 should be equal to 25. So I'm going to calculate that. 2x minus 5 equals 25. I add 5 to both sides, so I get 2x equals 30. Divide by 2. 30 divided by 2 leaves me with 15. Okay, so I was told to solve for x. X happens to be 15. Now in this case, if you were to plug x back into 2x minus 5, you would get 25 just like you get in the other matrix. Now, to solve for the y's is a little different in that this element and its corresponding element both have y in it. Okay, so when I set up my equation to solve, it's going to look like this. 3y plus 12 equals y plus 18. And I solve this equation like normal. So what I would normally do is I would subtract y, giving me 2y plus 12 equals 18. I would subtract 12. 2y equals 6. Divide by 2, leaving me with y equals 3. Now in this case, if you wanted, you could plug that back in, although I wasn't asked to specifically in this problem. And you could find a numerical value for that fourth term, or fourth element, I should say, in your matrix by plugging 3 back into either